I've done a lot of micropile work in the state of North Carolina through the years. I just wanted to mention real quickly, I did a big project in the late 90s with Ralph Sanders of F&R in Chapel Hill, the UNC Women's and Children's Hospital. In the early 2000s, I did the Western Wake Medical Center in Cary with Dan Schaefer of F&R, and then a lot of other projects with Andy Frank. And then I did a micropile project in Raleigh for a student housing high-rise with Ed Hearn at Geotechnology. So I've been registered, I think, as a PE in North Carolina since 1988, and it's one of my favorite states. And looking forward to getting back there next week for the Geo Congress. This project was done several years ago. It started, most of the production actually was done in 2014. It's a very interesting project for a lot of different reasons. I think you'll agree with me as you see here. The project's called the International Marketplace. It's a replacement of an older setup that was on this land for many years that it included the original Duke Kohanamoku restaurant and a few other restaurants, but it had evolved into a sort of a small vendor, trinket, Hawaiian souvenir, small restaurant, fruits and vegetables type place. And it was purchased by Saks Fifth Avenue, who developed this mall that we're going to talk about. It was actually a pretty unpopular project originally because the original International Marketplace had a lot of charm, but now that the new place is there, it's actually quite popular. So this is the outline of my presentation that you can see here. I'm going to go through all these various topics and talk about how the project went. It was not without its hiccups and challenges. So if you're not familiar with the island of Oahu, Waikiki is on the southeast side of Oahu, just to the southeast actually of Honolulu as well. So it's down here. Waikiki Beach is actually a man-made beach. This was a swamp area 75 years ago. It was dredged out and dredged sand was placed in there. So it's not a natural beach, but it's a very beautiful beach. And our project site is located in this little ellipse here shown on the map. This is part of the geotech report that was generated by a company called GeoLabs out of Honolulu. But it's about one block off the beach in Waikiki. And so the objective of the project was a deep foundation system and the redevelopment of the old marketplace, and Saks Fifth Avenue was driving this bus. The owners were Taubman Centers. They're a big mall owner out of Bloomfield Hills, Michigan, and Coastwood Capital Group out of San Francisco. The reason that deep foundations were required was there's an ancient buried alluvial valley that runs through this site. You can see the cleared construction in the lower right-hand side here when we're getting ready, when they were doing the demolition to begin the project. But the essential feature is a buried alluvial valley that has 180 feet of plastic clayey silt with blow counts from about 1 to 6. And so that's a pretty ominous feature in geotechnical engineering. Basically jello for 180 feet through the center of this site. And we'll talk much more about this as we go along here. Originally, when they asked for bids, the owner and the general contractor, who was out of New Jersey, asked for auger cast piles. And we looked at that. We declined a bid because at that time, and it's still quite difficult, it's really hard to make an auger cast pile longer than 150 feet. And so we're going to be leaving 30 feet of that clayey silt under the tip of your auger cast, and we just didn't see that as working. So we declined to bid. We sent them a note, as did another contractor, and said, hey, you know, we think we've got a better idea. It may not be as cheap as auger cast, but it will work, because we're predicting that auger cast is going to settle anywhere from 12 to 18 inches. So that got their attention, and we got a meeting with them to talk about it, and our price was better, much better than the drilled shaft price. So so one of the other problems with the auger cast, they had some good engineers involved, geotechnical engineers from Michigan, and who had looked at the auger cast and done some settlement predictions, and they didn't understand how we were coming up with 12 to 18 inches. If you look at this foundation plan, it's a pretty short mall. Most of it's only 2 stories. The SACS is like 5 or 6 stories with a parking deck, which is up on the northern side here, the SACS and the parking deck. But you can see how closely spaced all of these foundations are for this low-rise mall. And so what we calculated was that you were going to have overlapping stresses from these pile groups, where if you had a little particle of soil in the middle of these 4 different foundations that I'm showing here with the laser pointer, excuse me, you would actually have 4 times the stress in these deep soils, because you were so deep in the ground, and that just multiplies your foundation problems, or your foundation stresses, and creates the problems that we were describing to them. So they had a couple of auger cast bids. One was from Hawaii, one was from a company in Alabama, and 18.5 million was their low bid on the auger cast. But if you look at, this is from the FHWA manuals, you know, this is the typical, depending on stress distribution, depending on what type of soils and what kind of layering you have, et cetera. And, you know, we showed them that if you look at, you're a piece of soil down in this area, and you've got another foundation right next to it, that stress could overlap. And so we were actually with a bid of about 21.5 million, awarded a design assist and test phase contract to go there ahead of time and do a test program with 1 drill rig and a small crew. And then we did a design assist with the structural engineer, who was Ludwig out of Portland, Maryland, Portland, Oregon. Great structural engineer, very innovative. So it's a beautiful development. This is the artist's conception design concept. It's between Kuhio and Kalakaua Avenues, which is just a block or 2 off the beach. And these are some of the initial sketches that they made. This is the Kalakaua Avenue entrance. It's really beautiful. This is where SACS is located, with a parking deck up above that you can see here. And then the mall has 2 open indoor court areas, one for a big old tree that's been there for over 150 years. And then this is called the Queen's Court. This is on the northern side of the mall, but really pretty, as you can see here. And it came out looking pretty much exactly like this. So initially, they had some older borings that were from 2003 that they plotted up. The problem was that there was a lot of existing structures there and a lot of demolition that had to take place, and also some asbestos abatement. And so really, by the time we really got started, all we had were borings on the northern end of the site. We couldn't go below this line over here, except for you know, 1 old boring that was located down there, et cetera. But the boring showed this alluvial valley approximately in this location here. It kind of curves through the site. It's really one of the reasons why this site had never been developed before, because in 2003 they investigated it, and the Deep Foundation estimates were so high that they couldn't make this work. And so this was a really big development that had to be put together in order to afford this type of foundation system. So we made some recommendations for additional borings shown in red here, which were ones that they could get to at this time. So this is a sort of a rough outline of where that alluvial valley runs throughout the site. You can see it encompasses, more than half the site. I want to point out too here that there's a cross section AA that runs from north to south. If you can see this line here that we're going to look at here. So this is the cross section that shows these alluvial lagoonal deposits in this sort of burnt orange color. And this is that soft clayey silty clay with N values less than 6. The yellow materials are a coral or a coralline material. It can be highly variable. Number one, it's pretty permeable. The coral is all voided, etc. And some of it's infilled with clayey materials. And so it can be hard, it can be soft. It's highly variable. And then, so this is an old buried valley, that's been filled in through geologic time. There was some buried alluvium in here that's over consolidated. And then this gray band that you see is actually a basalt layer from a volcanic event. This site is not too far from Diamond Head. It's just to the northwest of Diamond Head volcano. So during one of those eruptions, this basalt was deposited in this valley at some time. And it's a pretty hard rock. It's a good rock, but it's pretty thin, as you can see here. And so we were actually targeting the basalt or the harder coralline layers for our deep foundation support. So when you're working on a project like this, there were several constraints that we had to take into consideration. Number one, working on an island in the middle of the Pacific is not ideal for material supply or personnel for that matter. Also, this is a very high tourist area that we were going to be working in right in the middle of Waikiki. It was surrounded by high-rise hotels. And so these hotels, which had been built decades ago, were founded on driven piles. And driven piles would have been a cheaper way to go on this project. The problem was that the hotels make a canyon that reflects sound tremendously. And so the city of Honolulu does not allow pile driving in this type of situation. It's too disruptive to the tourists and the hotels. And that's why a drilled foundation system was the one that had to be used here. In addition, there were these old banyan trees. You can see this one here on the left. They're tremendously large, very old, and they were considered to be a religious location for original Hawaiian residents. And oftentimes, folks in the old days of Hawaii would be buried under these banyan trees because it was considered a religious site. And so there was an ancient burial ground, particularly around the large banyan tree at the entrance, that had to be very carefully dealt with archaeologists, et cetera. Whenever we had to dig, it all had to be pre-dug and pre-approved. Also, the phased demolition that I mentioned, because of not having some of the areas available, particularly on the south side of the site due to asbestos abatement, et cetera. This was a real tough thing to deal with, not having the whole site available. And it was just in general a very congested site, as you can imagine, in the middle of such a big tourist downtown area. So this is the big banyan tree. It's actually on the National Register of Historic Plants. And if you could mute there, please, somebody's microphone, thank you. It's thought to have been there since about 1850. It's highly protected. It's, as I mentioned, it's considered a religious site to the indigenous folks. And during the project, there was a full-time on-site arborist who looked after this tree and some of the other plants in the area. There was actually a second banyan tree as well to the north that were originally proposed to be saved. However, that second banyan tree was inhabited by billions of wasps, and it was. Could you mute your phone, please? Thank you. So it actually had to be taken down, and it was going to be in the Queens Court area, but it had to be removed, and other plans were made. So we couldn't mess with the banyan tree, couldn't hurt it. In addition to that, so the big one's on the left here, the second one that was actually taken down was on the right. There were monkey pod trees. This is considered to be an invasive species from the Philippines. It was brought to Hawaii. You're not allowed to grow them anymore. And so with losing this other tree, they decided to use this monkey pod tree, but it had to be relocated over to the Queens Court that's shown here. So that was quite interesting as well. So in our final design for the micropiles that we came up with, we had almost 700 piles. They were either 200 or 300 kip piles. Most of them were 300 kip. The 200 kip were 5.5-inch diameter steel pipes. The 300 kip were 7 5/8-inch diameter steel pipes with 25-foot bond zones below that were reinforced with either 2 1/4 or 2.5-inch grade 150 thread bars. So there were some other piles as well. We had a few that had tension design, 45 of them that had tension design based on the structural engineering requirements. There were 6 piles where we did some soil mixing. They had real high lateral loads, so we soil mixed a big block around them to increase that. The piles had 4,000 PSI cement grout in them, and we had to proof test 5% of them, which was a big deal, as you can imagine, with 700 piles in the final design. So this is what the micropiles look like. I'll show you some installation and talk more about the installation, but basically they were drilled, they were quite deep. The longest pile that we put in here was 314 feet deep, very soft area in one part of the site. The average length was about 165 feet, but there were a lot of them that were in the 200 to 250, 275 foot length. So that's a tricky thing with such a small diameter pile. The great thing about micropiles, though, is that we can drill through anything. We went through the silt like butter, but then we had to drill through hard coralline layers, basalt, etc. And both of the pile cross sections had a 25-foot bond zone that was reinforced with the steel bar that you can see here. And so the smaller 5.5-inch were the 200 kip, the bigger 7 5/8 were the 300 kip. And these are pretty typical of the ones that we do all across the country in North Carolina, etc. So how do we put those piles in? Well, we flush them in with water. We use the steel pipe that will become the pile as our actual drill tooling, as our casing. There's a throwaway bit on the end. And so we would flush those in until refusal, or until we were in an area where we knew what we were drilling in and got down to the bond zone. So once it would refuse, we'd put another set of drill tools inside the pipe that had a tricone roller bit on it. We'd extend that 1 foot in front of the casing teeth, and then drill out the bond zone to about 25 feet in length. But we also measured how hard the material was, and I'll talk about that more here in a moment. Once we got to the target depth, we would set the thread bars in with, and also include a flexible Premi tube to pump cement grout in from the bottom of the pipe up. And then we would then lift the casing or the pipe up 25 feet or 30 feet, and then plunge it back in 5 feet, leaving a lower bar reinforced bond zone. And so the grout was topped off after the casing removal, and topped off as needed throughout the project as it's set up. So this is just a view of flushing that pipe in using water flush. It takes a lot of water. It's about 80 to 100 gallons a minute. And so we used a lot of water on this project. In order to determine if we were in something hard, it's really hard to tell when you're so deep. And also it was critical for the pricing on the project and the length of the piles. We developed what we call a DAC system. It's a data acquisition system where we look at various drilling parameters, including the RPMs, the down pressure, the flush volume, and it's a proprietary system that we put together, and we're able to use or calculate what we call the drilling index. And so this was controlled by a computer system on 2 of the 5 drill rigs. And we would go into new areas and explore it with the DAC. If we had something that was anomalous, we'd bring a DAC rig over next to the rig that we thought was anomalous and drill next to it. But basically what you see here is the output of that DAC system. And so this is just penetration rate in the red that you see here. And so every time we changed a rod, you know, obviously the penetration rate would go to 0. So each one of these is like a 20-foot because we use 20-foot rods. This is quite a long pile, you know, it's about 250 feet long. So we got through the lagoonal deposits. Then we hit this coralline layer here, you can see. So the drilling index is essentially 0 through the lagoonal deposits. We get a little bit of a drill index increase in the blue line here through the coralline. But then when we hit basalt, you can see that we've got some very hard materials here. And that told us that we were in the bond zone that was going to be able to hold the load. To develop that DAC system, we did a pre-production load test program that started about 4 or 5 months before the project, where we sent 1 drill rig and a crew over, and we did 8 load tests. We did 6 tension tests, which are much less expensive than compression tests, on various locations on the north side of the site that we could get. And we also did 2 compression verification tests. The tension tests were run to 150% design load. The compression tests at 200% design load. We did creep testing to make sure we held the load to make sure that we weren't getting a creep of the load over what we would expect. And then that was all assessed as far as how long the bond zone had to be. We had guessed at a bond zone number and this bond stress number, and we came in slightly above that, so that was perfect. And it also helped us to hone our grout procedures. It can get very hot there, and we could experience some flash setting of the grout. And so we had to figure out a few things, including using a super plasticizer water reducer to decrease the viscosity of the grout to get it pumped properly. This is the site of one of the initial load tests, and you can see the cutout area here. And so that any area that we did these tests on had to be pre-cleared by the archaeologist for iwi. Iwi is the Hawaiian word for bone, and it really means grave site. So they had to pre-dig any of these locations to make sure we weren't disturbing a grave before we did any of this testing. So this is one of the sites where we did that. And this is pre-demolition as well. So when we were doing that test, you can see here we have our drill rig we brought in, which is a pretty darn big rig. It's a Casa Grande C14 that weighs about over 100,000 pounds and has a 14-meter mast on it. And so we had to snake that in and run these tests in very confined conditions that you can see here. So we were able to do that. And then the pile load tests were run on various locations across the site, and you can see the variation in depth here of the piles between 84 and 204 feet. And so we had various locations with various testing methods, tension and compression, and then various pile lengths, which was very important for the structural engineer to know how much deflection they were going to get on these very small diameter long piles. Keep in mind that an auger cast pile would also deflect pretty significantly as well. Even drilled shafts at this length have some deflection, you know, over an inch, something like that. So this is just a view of one of the compression tests. We had to drill in 4 reaction anchors as well that you see on the corners here. So these are tie down anchors. And then the test pile is here. We're holding it all down, and we run that test to 600 kips. This was one of the 7 5/8 piles with a 300 kip design load. And then this is a tension test from an 84-foot long micropile, a very short one. And what we're noticing here is very linear response. It's basically a steel rubber band that it goes up and it comes down, right? So very good bonding. And of importance is that design load of 300 kips, we're getting about 1.5 inches almost of deflection on an 84-foot long pile. Then on a 201-foot long pile in a tension test, you can see here at the design load, we're getting 3.5 inches of deflection. So that was something that the structural engineer had to pay attention to. He did. And they were able to design into their system this type of deflection. So as long as they knew what kind of deflections to anticipate, they incorporated their slabs into the foundations in some locations, that type of thing. Very innovative design, but you know, just because you're not getting a 1/2 inch deflection doesn't mean you can't make it work. And in this kind of foundation condition, we really had to think outside the box, and they did a great job of that. So as far as the production phase of the project, after we finished the testing program, the design assist, and the final design, we started in May of 2014. We brought in 4 additional drill rigs. We had 5 there with the Casa Grande. They were Comacchio MC22 and 28 rigs, brand new from Italy. 2 of them were equipped with the data acquisition system, and we were clicking along at about 5,000 linear feet of pile per week, keeping in mind that we had to also have a separate crew doing these 35 proof tests that were required for the project. So it was going pretty well. This is the foundation plan that I've showed you before. There were a lot of foundations and a lot of different pile cap sizes depending on the load here. It's hard to see here, I'm sure, so I've blown it up a little bit. This is just one of the sections of the site. And wherever you see an ellipse around here and here, these are locations where the geotechnical engineer decided they wanted to do proof tests. And so they were pretty evenly spaced around the site. Some of them were in the buried alluvial valley, some of them weren't. And this just shows all of the different piles, locations, pile caps, etc. So you've got 5 piles here, 4 piles here, etc. This is another part of the site. Some of the 5.5 inch piles were around the perimeter, the lighter 200 kip piles, but basically the same thing. You know, you've got a big cluster here. They're going to do a proof test here. They're going to do one here. They're going to go over here, etc. And so we were able to follow along. Down here is a proof test here, and you know, big pile caps around these certain areas, smaller pile caps around the edges, etc. So this is just a photo of the production. You can see here, we've got the Comacchio rigs, which are sort of a gray colors, one here, one here, one here. And then this is the big Casa Grande C14 back here. And we're moving along. Here's a already drilled pile cap shown here, but a pretty congested site, but organized, and everything moving along fine. This is just a photo of the tremie grouting, where we put our flexible tremie tube all the way to the bottom of the drill hole. You know, this is like a 200 to 300 foot long pipe, and you can see the cement grout. It's a very thick water cement ratio of 0.45, which means it's a non-shrink grout at that low level. It also has the super plasticizer water reducer in it. You can see it's a very thick pudding looking material that's being pumped to the bottom of the hole. We fill or to the bottom of the pile. We fill the pile up from the bottom up. We use 20-foot steel pipe lengths here because we could. And you can see this line of drill rigs all along the line here. And we use these rod handlers for safety and production. So they're mounted on a small backhoe like you see here, and they're able to grip the pipe and set them in place. It reduces our crew size and is very safe and efficient. We also supplied the entire site, all of the drill rigs, all of the piles, 5,000 linear feet a day with one batch plant. So this was a huge automated batch plant that we brought in. It's Italian and quite efficient, and we were able to make grout and keep up very well with the requirements of the drilling rigs with this one unit. So very high production unit. You have to maintain it, keep it clean, obviously, on a daily basis, but it did a great job for us. We also produced pile installation logs, obviously, for every pile. This is an example of one here where the driller puts in, what he encounters at what depths. We talk about how much, what the times are. I didn't mention that the groundwater table is only at 5 feet on this site. It's only one block off the ocean. So the groundwater table is very high. And so with drilling with water is important to keep that head level high in the drill hole. And that's what we did. And so this has all of the drilling and grouting and reinforcing records. And we had a master tracking sheet for this and Excel sheet. We came up with daily reports. We took more than 8,000 photographs while we were there. And then we had very extensive weekly meetings between the Keller, or Hayward Baker at that time, staff, and also the owner and his design team, structural engineer, construction manager, et cetera. So it was a very great teamwork project overall. Just another shot of the production. You can see the rod handling rigs, one at each drill rig here, here, and we're moving along. Just another shot. Here's a test going on while we're drilling in other areas. We're running a confirmation test there, verification test. And this is just a close-up of one of those tension tests. We would include a full-length bar all the way from the bottom standing up in the air for these tests, and then pull on these piles. Obviously, it's a compression design primarily, but micropiles work equally well in tension or in compression. And if you think about it, it's actually conservative to test it in tension because you're not taking into account any end bearing, although it would be small. But it's a conservative way to test them. And so we recommend, these tests are only about $5,000 a piece. A compression test, because you have to install 4 reaction anchors, et cetera, are more like $30,000 a piece. Most owners will go with this, and it's conservative and it works great. So when we were working around the banyan tree, the old one in the front, we had to very carefully have the arborist. They would dig the hole out. In some cases, they had to very carefully trim some of the roots, but we weren't allowed to hit the tree in any way. This is around the outside perimeter. There were lots of foundations around the banyan tree. And then right under the banyan tree, we brought in a smaller drill, an MC 602 Kamakio rig that only had about a 15-foot mast on it, or 20-foot mast, and we were able to get in under the banyan tree where required. This is a funny photo. As I mentioned, they had to move the monkey pod tree, and so the general contractor brought in a crane. They excavated all around it, and they picked it up and moved it over to the north side of the site, very close to the site where they had to demolish the other banyan tree. So that monkey pod tree is still there, alive and well. And this is just a view of a pile cap where we've got 5 piles in a linear crisscross configuration. These are 7 5/8. You can see the bar coming out of them, and these will be cut off at foundation grade when they're ready to pour the pile caps. This is a pile cap with a 5.5 inch with only one tension pile in that location. It is in the corner there. That's why it has a bar, but a typical 9 pile cap with the smaller piles. So everything was going great. And then on October 28th, we drilled a pile, and the guys grouted it, and we had to turn all the engines off at 5:15 and be completely quiet by 5:30 p.m. every day. And so they finished grouting the pile. It was a couple 100 feet long, and they left the clamps on the pile from the drill rig, and left the drill rig sitting there for the night just to hold it in place while the grout set up. And they measured the depth of the grout, and it was down about 20 feet or so inside the pipe, which wasn't unusual because of the coralline bedrock being very porous. And keep in mind that the grout has a specific gravity of about 1.8 to 1.85, much heavier than water. And so we would typically top those off the next morning. So they measured the depth of the grout. They went home, had dinner. Everybody came back the next morning. And the first thing the driller did was fire up the drill rig, and he released the clamps, and the pipe disappeared. It fell down in the hole 25 feet. So that's not supposed to happen. But one thing that they noticed before he did that was that the grout level inside the pipe had risen 43 feet overnight and had spilled over the top of the pile. And how is that possible? You know, it was something that we couldn't get our heads around. And then after talking about that with this very experienced driller who still works for us up in Tennessee, he said, well, that happens all the time. And I said, what do you mean? Or the team said, what do you mean? He says, yeah, the grout will come back in and the grout will be higher than when we left it. And I said, well, why didn't you tell us that? He goes, well, I just figured it was because we were grouting piles all around it and all that grout was getting pumped to the ground or whatever. So that was quite a conundrum. And so what we figured out was, apparently because Diamond Head is so close and there are all these underground lava tubes, that there was incredible artesian groundwater pressure that was able to push a 180-foot grout column up with a specific gravity of 1.8. So you're talking about incredible pressure. It was pushing up, and you know, it was unbelievable. So we started looking at it, and we were talking to the drillers and the project engineers. Where did this rise happen? And so they had noted that in most locations. They just hadn't told us. They were on the installation sheet. So we went into a mode of, we got to figure out what's going on. We were 78% complete. 544 piles were in place. They'd already started placing pile caps on some of these piles. So we brought in an engineering team. We notified our client immediately, and we went through all of the records trying to find grout rise wherever it had happened, but the data was sporadic. They had not noted it in all locations. So we looked at other potential risk factors. We were worried about our piles, and we were worried when the grout head versus the water head was within 15% of one another. We were worried about piles where they had grout takes of 350% over the neat volume anticipated, and obviously ones that were where grout rise had been noted. So production stopped. We made up a list and found 95 piles originally that met these 3 criteria. In the end, we increased that to 116 piles, which is 22% of the overall pile volume. So incredible problem. So this is a map that shows the suspect piles. They weren't necessarily in the alluvial channel. Some of them were, obviously, but a lot of them were on the north side. And we also found out that Waikiki is a Hawaiian word. Wai means fresh water, and kiki means splashing up out of the ground. And so it basically means artesian wells. We also found that for 80 years, all of the hotels around this site, we didn't know this before, had been supplied by artesian wells. They didn't even know where the wells were anymore with all the development, but they hadn't had a water bill in 80 years. And so this was a tremendously artesian area, and it wasn't mentioned once in the geotechnical report. So what we decided to do was to take all these suspect piles and to drill them out. So when we drilled them out, about over 50% of them were fine, but there were many that were not. And so these were the non-compliant locations that you see here. So suspect, non-compliant. And so you can see here that some of them are in the alluvial channel, some of them aren't, but definitely there was more artesian pressure to the northern side than the southern side of the site, although we had a couple bad ones down below as well. So we verified each one of these piles by drilling them out. We drilled the bar and the grout out of the bigger piles. We cored around the 5.5 inch. We extracted the bar, and then we consolidation grouted these piles where necessary, reset the par, and tremi-grouted them. And so, unfortunately, we recognized that we could have some grouting problems with such deep depth, et cetera. And we had a price to consolidation grout and re-drill, but our project manager was trying to save the client money and just took it a little too far. We should have done consolidation grouting, and she was trying to hold the price down and probably shouldn't have done that. And so we learned a lesson there. So here's sort of a summary of the remediation work. 46 of the piles we drilled out were fine. We just re-grouted them, put the bar back in. 66 or 12% were not fine. We found either soft grout that had been overwatered or voids. 4 of the piles we just replaced didn't even consider it. They were in locations that were part of the schedule that couldn't be varied. But we consolidation grouted to the tune of 10,300 cubic feet of additional grout that basically was filling up lava tubes and keeping that water pressure away from our piles. You can see here on the right, one of the drilled out bars where it had bonded to the coralline down below here, but you see a bare bar. The grout had been washed away from the bar. We were afraid of this. And then the drilling process had disrupted the centralizers that were on 15-foot centers, but drilling it out had scooted those around. There's just a close-up view. You can see a bare bar, and then closer where the coralline had bonded to the grout. So we had to fix them. And some of the piles were already under grade beams. And so we had to chip out grade beams to check piles. And so the general contractor was great. He obviously charged us from some delay to the tune of a couple $1 million. But hey, you got to do what you got to do, right? It's got to be right. So, you know, there was a congested site at this time. We had to get, we brought another drill rig in from the States. So we had 6 rigs, and we went to work. It was challenging, and we had to extend the project schedule for us for another month. And so lessons learned are, if you're in really high grout take soils, you should consolidation grout and re-drill the hole. Have a plan when drilling in dynamic or artesian groundwater. Installed micropiles can be remediated. They can be drilled out. And if you're a field engineer or a young engineer and you see something that's unexplained phenomenon like grout rising in a pipe, tell somebody about it. So we were supposed to be done on December 22nd. We ended up completing on January 7th, which was great. We had to use a lot more grout. We were paid for the consolidation grouting and redrilling because it was in our contract to begin with, but we were not paid for extending the time or chipping out the pile caps, etc. And so incredibly, we were able to almost meet the schedule and still remain friends with the general contractor. So these are some of the statistics. All of the proof tests passed. We had thousands and thousands of grout tests. Only 2 of the grout samples did not pass the 4,000 PSI. We began remediation work on January 7th, and we were done by the 1st of February with our 6 drills. We had started to demobilize. We canceled that, and we brought in more crew. And so this is what the project looks like. You can see the banyan tree in the open court here. There's an open courtyard area. This is Queen's Court, named for Queen Emma, the Queen of Hawaii in the 1800s. This is the Saks Fifth Avenue with the parking deck back here. The ocean is at the bottom, about a block away. Here you see an aerial view looking towards the ocean. Here's Waikiki Beach. There's the banyan tree, the Queen's Court, etc. And so the project has been in place now for many years and is a beautiful location. This is the actual, not the artist's conception of the entryway there, with all the palm trees they put in. And as mentioned, it won the 2016 Kapp Foundation Institute Outstanding Project Award, which is really great. And then from inside, this is the entrance of Saks Fifth Avenue from the interior of the mall. And this is the Queen's Court. This is a statue of Queen Emma here. This is a little stage where they have Hawaiian hula dancers and various other performances, live music. There's our flying monkey pod tree in the back there, which is doing great. And that's it. I appreciate the opportunity to present, and I'd be happy to look at the questions. Thank you.
Thank you very much, John. Very interesting presentation.
Thank you.